Okay, thanks. Well, thanks a lot for coming here. And last year, I met many great people in this place. And this year, I'm meeting more great people. So please come to us, especially if you have questions. And so I will start off with about the wireless precision time synchronization. And so quick. Sorry for those who have seen this slide for 1,000 times, but this is a sort of applying the two-way satellite time and frequency transfer into the regular commercially available wireless communication devices. So the same principle is applied, and basically we do the two-way time and frequency transfer. And Satoshi Yasuda is the one who made this all come to life. And it is a 920 megahertz wireless communication module. And it is fully compatible with the IEEE standard. So it can transmit and receive the signal. And range can be order of hundreds of meters or 5 kilometers. And even in US, you can put 1 watt. So you can reach 5 kilometers easily. And the accuracy is, clock accuracy is 30 nanosecond with 16 picosecond jitter. So this is the sort of first demo video that we made. And, sorry. So normally each module have its own clock, but the frequency is usually off, so you see the drift on the oscilloscope. But with the WiWi measurement, you feed back the error signal to the oscillator, and now two oscillators are physically phase locked over the air by communicating over the radio. And we can expand this to the multiple devices, and we can even get the PNT, position navigation, as a sort of byproduct of the synchronization. And with this demonstration, you can see that the two modules are connected to the helmet, and two modules are stationary. And Satoshi is going to ride this vehicle. And on the left is the measurement with WiWi, and on the right is measurement against the laser rangefinder. And you can do this kind of real-time measurement. So this is not just synchronization, but it is really PNT measurement all by itself. And so we are, since this is OCP, we are applying this to the data center. And I don't think data center will be sort of wirelessly synchronizing all the servers, but if you want to make some application that has to do with user experience, you eventually need to synchronize to the user via wireless. As far as RU unit, you can synchronize over the wire, but from there, you definitely need to communicate with wireless, and you can do the synchronization and PNT if you want. So in sort of data center setup, the one setup we tried is this is one application that you imagine that you feed the signal from GNSS receiver at the top of the building and try to transmit the clock within the building so that you can avoid the wiring within the buildings. And so long story short, this start from the plot here. This is plus minus 1 nanosecond, and the green is the measurement flow of the Calnex device. So, and red is the synchronization level, looking at the 1 pulse per second, and you can see that it's a little bit above the noise flow of the Calnex Sentinel. And now this blue is the comparison between your input, external input to the external, output went through the wireless communication. And since our sort of feedback to match to the input signal isn't that good, so it's about 10 nanosecond, 12 nanosecond peak to peak over 10 days or so. But at least we showed the point that it works as a wireless sort of PPS in and out as a application. And another thing that we did is we put a small form factor. We fit all WiWi module into the RCB form factor, and it's actually functioning to do the synchronization. And we also demonstrated that it might lose the lock, but it autonomously bring it back to the right time even when it lost the lock. And so this is all I did is about the 200 megahertz, and now Aditya is going to talk about more cool stuff.
Sure. Thank you, Nobu. Okay, there you go. So yeah, whatever Nobu has done, I think really cool stuff, right, in terms of getting sub-nanosecond synchronization, PPB level frequency synchronization. But the question that we are asking now is, how can we continue to expand the access to this time synchronization across multiple devices, right, and as many devices as possible? So the first question when we think about this is, why do we even care about expanding this access, right? So let me tell you a few things. So the first thing is, when you think about the next 10 to 20 years, with the increase of number of IoT devices and other wireless devices, you'll have like over 10 billion devices sitting out there competing for the extremely limited frequency and time channel resources available, right? So how do you make sure that all of these systems can coexist in the same space? The answer is to precisely control their medium access, right? And the key to this precise MAC control is your time synchronization, right? So there is a need for accurate time synchronization at the end device. Apart from that, when you think about the next generation factories or even the next generation transportation infrastructure, you have multiple autonomous agents, multiple robots working together in collaboration, right? So in these kind of collaborative setups, what is really key, right? It's extremely important to get holistic worldviews of your space using the multiple sensors that you actually have in your hand, right? And to enable this sort of sensor fusion and this collaborative sensing, time synchronization and timestamp data again become extremely important and critical, right? And finally, in line with some of the demos that Nobu has showed as well, localization and ubiquitous localization in indoor environments, again, is becoming more and more important for safety purposes and other navigational applications. And even here, we see that leveraging a sub-nanosecond time synchronization across the localization modules can further improve the accuracies up to centimeter or even millimeter levels, right? So given that there is a large number of use cases, we do need to supply the level of time synchronization that Nobu is providing using other radio technologies as well. So as a starting point, it's always funny because the laptop is here, but I point the monitor towards the slides. Anyway, so given that Wi-Fi is one of those technologies that is so ubiquitously available on so many of the devices out there today, and it's like a leading technology for IoT services. It is a backbone network for many of the industrial robotics. And it is also a great solution to enable indoor localization because of its penetration in indoor spaces. So Wi-Fi, leveraging Wi-Fi is a great first step to actually expanding the time synchronization that we care about. So, did I? Okay, so so we have a few key goals that we would like to meet through the time synchronization work stream that is being headed up by Nobu and Julian. So the first thing is we would like to get the sub-nanosecond time synchronization that we care about, along with sub-PPB frequency synchronization, and we want all of this to happen over Wi-Fi compliant packet exchanges. Apart from that, we would like all of this to be off the shelf and open source, which is the ethos of OCP itself. And finally, we would like to develop some proof of concept core applications to kind of really show the world what we can do with this level of time synchronization. Because often what we start seeing, and this is maybe I can put this question back to the audience as well, is what are the applications of some of the things that we're developing, right? So that's a question that we often ask ourselves, and we don't have a strong enough answer yet. So I'd love to get some of your opinions on that. So on that front, with Julian and Armando's help from Meta, we developed a test PCB which has two synchronized Wi-Fi ESP32 chipsets. They're synchronized with the digitally controlled oscillator from SI time, and it has a 10 megahertz PPS clock input and output as well. And we have performed some sanity checks on the channel state information acquisition. So this is the file layer information. We are able to get it at the application layer. We have also looked at the phase stability across packets to make sure that the measurements that we are getting can actually be useful. So with this, let's actually understand how we can solve some of the problems that we care about, right? So the first thing is correcting frequency offsets between a transmitter and receiver clock. So in a very simplistic radio diagram here, what you have is you have a clock along with the PLL, which generates the 2.4 gigahertz carrier frequency, which is then mixed with your data and then transmitted out into the world. And on the receiver side, the opposite happens, where a separate carrier frequency FRX is generated along from its derivative FCLK2 clock. And this is down-converted to give you some physical layer information. In this case, I call it the CSI, channel state information. But often what happens is if these two clocks are offset from each other, because during the down conversion process, you have some residual phase offset that continues to remain, which we can actually leverage to measure the clock offsets between the transmitter and receiver very accurately. And to the extent that we can actually measure it up to 5 millihertz of accuracy, right? And for a 40 megahertz clock, this turns out to be a measurement of approximately 1 part per billion. Actually, less than that. But the story doesn't really stop there. In like many of the indoor wireless applications, we don't not only have like a direct path of a signal going from the transmitter to receiver, but we often have some kind of reflection or multipath in the environment as well, right? Which can corrupt a lot of the phase information that we want to measure. So here, what we can take advantage of is the fact that Wi-Fi, unlike some of the things that we have used earlier with WiWi, is transmitted over a broad frequency band. And we can leverage the fact that different amounts of phase is accumulated at different frequencies when a signal travels to actually disambiguate the direct path and the reflected path. And there is a specialized transformation called music, which can be used to do this. But essentially, it can convert the frequency domain signal into something like a delay domain signal, right? Which tells you which is the direct path and which is the reflection itself, which can then be used to actually just separate out what you care about. So in this way, you can sort of get the frequency offset calibration, measure it, and also handle a lot of the challenges that exist with wireless transmissions itself. So from here, this is still a in-progress project, right? So the next thing to understand is how can we actually characterize some of the time offsets that exist in the clocks itself, right, apart from the frequency offsets. And additionally, how can we take these measurements that we are making and develop a closed-loop system to discipline the onboard oscillator itself that we have? Because currently, we have a digitally controlled oscillator that we can tune through a third ESP module. And finally, like what I want to throw back again to you guys is how can we expand this to other radio technologies, including LoRaWAN or BLE or even other RF systems, right? And yeah, with that, I would like to take any questions. And if you, I'd like to leave this up. And yeah.
All right, let's go with questions. Question? No? OK, if you have a question, OK. Here comes one.
My question is for both of you. Would you consider a one-way timing transfer so that you can maintain privacy? Like if a user was to enter a space and they didn't want to share their information, the location, having a one-way time sync, would that be something you guys would
Yeah, I think that's a very good question. So for some of the frequency offset computation, that can actually be done from a single transmission itself. Really, what we are seeing is a two-way is required to further eliminate the effects of the environment. But then, yes, I definitely agree on that end.
So that's really interesting question. And so we can choose to whether put all the calculation resource onto the or the base station side or user side. And if you allow to have the user to be capable of computing, then what you can do is suppose we have more than 4 base stations around you, and they are communicating via wireless to synchronize. Actually, you can just passively receive, and by calculating like a GNSS, you can actually at least calculate the time. And if you know the sort of all the data, actually you can calculate the position relative to all those base stations as well. So but in many like IoT sensor application, you don't want to put a lot of computing power to the device, but in the application, you care about the security, and you can afford power for calculation power. Then there are things that you can do.
All right, thank you.